കോർഡിനേഷൻ കോമ്പൗണ്ട് എന്ന മൊഡ്യൂളിലെ സെക്ഷൻ സി ക്വസ്റ്റ്യൻ ആൻസേഴ്സ് ആണ് ഡിസ്കസ് ചെയ്യുന്നത്. ഫസ്റ്റ് ക്വസ്റ്റ്യൻ എ, എക്സ്പ്ലെയിൻ വിത്ത് ദ ഹെൽപ്പ് ഓഫ് MOT ദ ബോണ്ടിങ് ആൻഡ് മാഗ്നറ്റിക് കളർ ക്യാരക്ടറിസ്റ്റിക് ഓഫ് കോർഡിനേഷൻ കോമ്പൗണ്ട് എന്ന മൊഡ്യൂളിലെ സെക്ഷൻ സി ക്വസ്റ്റ്യൻ ആൻസേഴ്സ് ആണ് ഡിസ്കസ് ചെയ്യുന്നത്. അതിലെ ഫസ്റ്റ് ക്വസ്റ്റ്യൻ എ, എക്സ്പ്ലെയിൻ വിത്ത് ദ ഹെൽപ്പ് ഓഫ് MOT ദ ബോണ്ടിങ് മാഗ്നറ്റിക് ആൻഡ് കളർ ക്യാരക്ടറിസ്റ്റിക് ഓഫ് CONH3 6 3+ ആൻഡ് COF6 3-. അതിൽ ഫസ്റ്റ് CONH3 6 3+ നോക്കാം. ഇൻ CONH3 6 3+, CO3+ present is a 3d6 ion. There are a total of 80 electrons, 6 from CO3+ and 12 from the 6NH3 ligands. NH3 is a strong field ligand, so energy difference between T to G and EG star is greater than the pairing energy. Molecular orbital configuration of the complex A1G2 T1U6 EG4 T2G6. The complex ion is a low spin complex. All the electrons are paired. The complex should be diamagnetic. T2G to EG star electronic transition can be achieved by adsorption of light in the blue region. The complex thus has the complementary color, namely orange. Next, COF6 3-. In COF6 3-, CO3+ present is a 3d6 ion. There are a total of 18 electrons, 6 from CO3+ and 12 from the 6F- ligands. F- is a weak field ligand, so energy difference between T to G and EG star is smaller than the pairing energy. Molecular orbital configuration of the complex A1G2 T1U6 EG4 T2G4 EG star 2. The complex ion is a high spin complex. There are 4 unpaired electrons. The complex should be paramagnetic. T to G to EG star electronic transition can be achieved by adsorption of light in the red region. The complex thus has the complementary color, namely green. Second B question, briefly discuss the merit and demerit of MOT of complexes. Merit of MOT: provides a clear understanding of the electronic structure of coordination complexes, helps explain the magnetic and color properties of complexes, allow for the prediction of the stability and reactivity of complexes. Demerit of MOT: oversimplifies the complexity of coordination compounds, does not account for the effect of ligand-ligand interactions, can be difficult to apply to complexes with multiple metal centers. Second question, discuss the various factors that affect the stability of complexes. 1. The nature of the central ion. In general, the greater the charge density on the central ion, the greater is the stability of its complexes. In other words, the greater the charge to radius ratio of central ion, the more stable its complexes are. Example, Fe3+ and Fe2+ have more or less the same size, but the charge on the Fe3+ is higher. The charge density of Fe3+ is thus higher, and hence its complexes are more stable than those of Fe2+. The general stability of complexes of the divalent first-row transition metals ions from Mn2+ to Cu2+ is found to increase in the order Mn2+ less than Fe2+, less than CO2+, less than Nickel2+, less than Cu2+. For the above ions having the same charge, ionic radius decreases from Mn2+ to Cu2+. Consequently, the charge to ratio increases in the same order, and hence the stability of their complexes also increase in the same order. Second point, the nature of the ligand. അതിൽ എ ബേസിക് സ്ട്രെങ്ത്. ദ ഗ്രേറ്റർ ദ ബേസിക് സ്ട്രെങ്ത് ഓഫ് എ ലിഗാൻഡ് ദ ഗ്രേറ്റർ ഈസ് ദ ഈസ് വിത്ത് വിച്ച് ഇറ്റ് ക്യാൻ ഡൊണേറ്റ് ഇറ്റ്സ് ലോൺ പേയേഴ്സ് ആൻഡ് ഹെൻസ് ദ ഗ്രേറ്റർ ഈസ് ദ സ്റ്റെബിലിറ്റി ഇറ്റ്സ് കോംപ്ലക്സസ്. ദ Cn minus F minus NH3 etc. are good bases and form many stable complexes. B. Charge density. The greater the charge density on a ligand, either greater the Tack charge to radius ratio of a ligand, the greater is the ease with which it can get to the central ion, and consequently the greater is the stability of p complexes. Example, among the halide ions all have the same charge -1, but their size vary in the order F minus greater than Cl minus greater than Br minus greater than I minus. As a result, F minus has the highest charge density while I has the least. The stability of the complexes involving the halide ions increases in the order F minus greater than Cl minus greater than Br minus greater than I minus. C. Capabilities for affecting back bonding. Ligands capable for accepting electron density into one of their vacant antibody orbitals through pi interaction, and thereby strengthening the metal ligand bond through additional pi bonding form very stable complexes. Example, Cn minus CO. D. Capability to form chelates. The chelate formed by bidentate and polydentate ligands are more stable than complexes formed by monodentate ligand. 3. Presence of chelate rings. Complexes containing chelate rings are in general more stable. Example, the chelate NiEn3 2+ is more stable than NiNH3 6 2+, which is not a chelate. The effect is known as chelate effect. Third question, discuss with the illustrative example the application of complexes in different form of analysis. Answer A. A qualitative analysis. In the separation of metal ion, if Cu2 plus and Cd2 plus are present together in solution, both are precipitated as sulfide in group 2 upon passing H2S in the presence of HCl. The normal procedure for group 2A analysis would involve dissolution of the sulfide Cu plus CDS in dilute HNO3 followed by treatment with NH4OH. Both Cu2 plus and Cd2 plus would form soluble amine complexes. The above solution is treated with KCN solution so has to get the soluble cyano complexes. Upon passing H2S, CuCN4 3- does not decompose on account of its high stability, but CdCN4 2- 2+ being not that much stable, it undergoes decomposition and gets precipitated as CDS. Second, in the identification of metal ions, several metal ions are identified from the colors of the soluble or insoluble complexes they form with complex agents. Example, when Fe3+ in solution is treated with potassium ferrocyanide, the deep blue precipitate of ferric ferrocyanide is formed. When Cu2+ in solution is treated with the excess of NH4OH, deep blue solution of tetraamine copper 2 ion is obtained. B. In quantitative analysis. First, in volumetric analysis. Titrometric methods based on complex formation are generally referred to as complexometric titration. One particular chelating agent that has found wide application in the volumetric determination of metal is ethylene diamine tetraacetic acid or EDTA. It is a hexadentate ligand which can bind to a metal ion simultaneously through 6 donor sites. Second, in gravimetric analysis. A large number of organic reagents capable of forming water-insoluble chelate complexes with the analyte species are used as precipitating agent in the gravimetric estimation of metal ions. 3. In colorimetric analysis and spectrophotometric analysis. Colorimetric analysis and spectrophotometric analysis are based on Beer-Lambert's law. Several transition metal ions, when present in trace quantities in solution, can be determined by such methods using reagents capable of forming stable, soluble, intensely colored complexes with them. The method involves measurement of the optical density of this dilute colored solution at appropriate wavelength. Since the optical density is directly proportional to the concentration of the species in solution according to Beer-Lambert's law, such measurement with standard solution and then with solution of unknown composition can lead to estimation the analyte ion